In this video, we're going to study autonomous differential equations. Okay, so what is an autonomous differential equation? Well, this is a generic differential equation, not yet autonomous, and it says that the derivative is just some function of the independent variable t and the dependent variable y. Sometimes the independent variable is also labeled x, that's okay. So the point here is that y is a function of, in this case, t, but t is just independent. So that's the generic case for a first order differential equation. So what makes it autonomous? Well, an autonomous differential equation is one where the t just doesn't appear. I mean, it's still a derivative with respect to t, and y still depends on t, but the explicit definition of the differential equation, it only depends on y. It's a derivative of y is equal to just some expression in terms of y. So our definition is that an autonomous ordinary differential equation is one where the derivative only depends explicitly on the dependent variable y. So here's an example. This is the derivative of y with respect to t is equal to 1 plus y times 1 minus y. That right-hand side only has y's in it. And one thing I want to note right off the bat is that if you were trying to figure out, well, when is the derivative equal to 0, then you'd get that y is equal to minus 1 and y is equal to 1. If you knew this was your derivative and you were in Math 100, you'd say its critical points were at minus 1 and 1, where the derivative was equal to 0. So now we're going to turn to the computer to help us graph it, and I want you to keep these two spots, y equal to minus 1 and y equal to 1, in mind. So I opened up my GeoGebra to plot slope fields, and I plugged in 1 plus y, 1 minus y is equal to y prime. And this is the kind of behavior that I get. So I want to notice a few things. First of all, recall that our two spots where the right-hand side was 0 was either y equal to 1 or y equal to minus 1. And what you'll notice is if you go along the line y equal to 1 up here, it's where the derivative is 0. And if it plotted at that exact point, you get horizontal lines. When y is equal to minus 1, that's down here at minus 1, it's going to similarly be this horizontal line. And so these are what we call equilibrium solutions. And the idea of an equilibrium solution is if you started at y equal to 1, if your value is exactly y equal to 1, then the derivative would be 0, and so you wouldn't change. And then you wouldn't change, and then you wouldn't change. You'd always be at the value of y equal to 1. That's why it's called an equilibrium position, because it doesn't change. And likewise for y equal to minus 1. If you start at either of those locations, then you just don't change at all. The next thing I want you to notice is that, well, this is a two-dimensional plot. So y is our vertical, and our independent variable, which is labeled here as x, is our horizontal. Well, that is a two-dimensional plot. It's sort of only actually one-dimensional because the x doesn't matter. As in, everything is exactly the same along any horizontal line. Like, take y equal to 0, for example. If I was to plug in y equal to 0, I would get a slope of 1. All the way along the line, the x-axis, which is where y is equal to 0, the slope is exactly 1 there. And if you go at any point, okay, how about 1.5? Well, 1.5 has a steep negative slope. But if you go along the values of x, if you fix the value of y and just change x, it's the same slope everywhere. So yes, it's a two-dimensional plot, but honestly, the information along the y-axis is really all that matters because it's just the same for every other value of x. All right, third thing I want you to notice. I can take this starting initial condition and I can move around where it starts. I may as well just go up and down the y-axis to be talking about x is equal to 0, what is the initial value of y. And if I'm in this region here where I'm in between the two equilibrium values, then all of the curves look the same. Basically, if you increase the value of the independent variable, you go up to the one equilibrium. If you decrease it, you go down to the other equilibrium point. So they all have that basic shape when I'm in between these two equilibrium points. If I was to go up above the equilibrium point, so that now I was bigger than the value of 1, you'll notice that all of these curves tend down towards the equilibrium point, but they don't cross it. So that's the big lesson here, is that when you've got these equilibrium points, you can't have a curve that crosses the equilibrium because, well, if it ever hits the equilibrium, it just stays at the equilibrium forever. And then the final thing I want to note about this is that the two different equilibrium points have a very different type of behavior. Consider the y equal to 1 equilibrium point. If I start, as I've done here, above that equilibrium point, I descend until I basically end up really, really near the equilibrium point. You can imagine that as time went to infinity, you just sort of settle down right onto that equilibrium point. It would be asymptotically would align with that equilibrium point. And then likewise, if you began a little bit beneath the equilibrium point, you rise up until you get to that equilibrium point. This is what we're going to call asymptotically stable. It basically says if you're nearby the equilibrium point, you're going to end up at that equilibrium point. Now contrast this with what happens if you start near the value of y equal to -1. I mean, I'm right here near the value of y equal to -1, but it sends you all the way up to +1 again. Likewise, if I start just beneath the value of -1, okay, I'm very close to that equilibrium point, but it sends you away looking like it's going to -infinity. This type of equilibrium point, where solutions that start nearby tend to go off in completely different directions, is called an unstable equilibrium point, as opposed to a stable equilibrium point like y equal to 1. Okay, so that's pictorially what's going on. Let's just write down these definitions a bit more precisely. Okay, so now let's write down those definitions precisely. We have here a generic autonomous equation. An equilibrium solution is a constant solution whose value is just a zero of the function f of y. It's a spot where f of y is equal to 0. And we're calling it an equilibrium solution because the rate of change of y at that spot is 0. And so nothing changes, it's just sort of static, and hence an equilibrium solution. And then what we saw is that there's actually a couple possibilities that equilibrium solutions can look different ways. One of them is they could be called asymptotically stable. And what we meant by this is that if you had an equilibrium solution y equal to a, and you started nearby a, maybe not exactly at a, but in some region around a, then as time went on, you're going to get closer and closer and closer to the value of a. You're going to tend towards the value of a. So this is when you have an asymptotically stable situation. It basically says if you start nearby the equilibrium solution, you're going to end up at the equilibrium solution, at least if you had enough time, as time goes to infinity. This was in contrast to an unstable equilibrium point. And an unstable equilibrium value is the opposite. If you start near the value of y equal to a, even if you start extremely close to the value of a, then you're going to leave the value of a as time goes on. And so equilibrium solutions are either stable or unstable. Now, the final thing I want to do is return to the equation that we've seen the slope field before. That's y prime is 1 plus y times 1 minus y. And to talk just a little bit more about the equilibrium solutions and whether they're stable or unstable. And this time I'm going to actually draw it out by hand as opposed to turning to the computer. It's actually not so bad when you have an autonomous equation, because recall that this only depends on y. So I don't really need to do anything more than draw the y-axis. I could draw the t-axis that would be going off to the right, but why? It's the same for all values of t, so let me ignore this. And then the next thing I like to do is I like to come here and put on the equilibrium value. So I have the -1 and the 1. Those were the two different equilibrium values that I found. And then what I really like to do is to look above and below every one of these equilibrium values and just say, what is the slope doing at that point? So let me start by looking at values bigger than 1, bigger than the larger of the two equilibrium points. For example, 2 as just a number. If I was to come in here and to plug in the value of 2 there and the value of 2 there, then what I would get was a negative number. And indeed, any value bigger than 1 is going to give me a negative because this right term is going to dominate and be negative. And the way I'm going to illustrate this is to go and draw a downward arrow when I'm above that first equilibrium point. So this is just indicating that my slope is negative, that it's going to be going down, that the values of y will be dropping. This is very reminiscent of what we did back in Calculus 1 when we were studying the critical points of a function, and we'd look to the left and the right and see whether the derivative was positive or increasing. It's basically the same idea. It's just that we have this larger context of differential equations. Anyways, if I go in between the two equilibrium points now, say a value like y equal to 0, I plug that in and that's going to be positive, right? If I plugged in 0 in for y there and 0 in for y there, then this indeed would give you a positive value. So what I can deduce is that the arrow is going up in this middle portion. And this is what lets me conclude that the point which is y equal to 1 is a stable equilibrium point. Because above and below the equilibrium point, the slopes are tending towards the equilibrium point. They're negative when you're above it and they're positive beneath it, which is going to send them to the equilibrium point. Finally, if you plugged in a number which was less than -1, so a number like -2, then what you get is something negative times something positive, something negative overall, the derivative is negative. And so again, it's an arrow which is going to be pointing downwards, and that's why y equal to -1 is an unstable equilibrium point because a solution that starts near there is going to tend away. All right, so that's my introduction to autonomous equations. If you have a question, please leave it down in the comments below and we'll do some more math.